right, good afternoon. Do we have everyone? 1, 2, 3. Missing still one, but that's okay because we're recording it. So whatever he missed, he can come back. Good. Today, so first of all, congratulations for surviving the last lecture. The last lecture was really long, right? That was 150 minutes, and that was quite long actually. But that was that was supposed to be the hardest and the longest lecture of all the lectures I'm gonna give in this course. So there's no need to be stressed out. It's not gonna be like that for every lecture. I'm going to try to alternate between quantum optics lab and quantum spin lab so that people who do quantum optics lab could also learn something from the lecture, and people who do quantum spin lab can also learn something from the lecture. There's no guarantee that the knowledge that you will be using for your experiment will be taught in the lecture in time. So because this lecture was not supposed to give you the full knowledge of whatever you need to do. This is like a more of like a supplementary material for you. In order to understand your experiment or writing your report, it will be necessary for you to at least read the manual. Okay, so for the quantum optics lab, we have the full lab manual, which is quite comprehensive and well written. For the quantum spin lab, we have two manuals. One is not so good and one is better. Yeah, remember? So I think the materials in the manuals can at least give you a first order approximation of understanding the physics. All right, and whatever is taught here is to help you enhance your understanding. All right, so this is for enhancement. All right, so last week we talked about quantum spin, nitrogen vacancy center. Today I'm gonna talk about classical and non-classical light. Okay, and I'm sure many of you heard of the word photon, right? But I don't think many know where this term derives from. We often think it as little balls flying in the air, and that constitute the light beam. That's the physical picture we are given most of the time. But is that an accurate picture? That's what we are here to find out, both through the experiment and through the lecture. Let's see if this is a valid picture. Maybe it is, maybe it's not. We'll see. Okay. So before we start with a difficult topic like that, let's start with something relevant, but simpler. Okay. So let's start with light source. Light source. Okay. So in your lab, if you remember, there are two types of light sources. One is called LED. Yeah. So it's just like this. What it emits is fluorescence light. Yep. And the other one is called laser. Okay. How many of you know what laser stands for? It's an acronym of 1, 2, 3, 4, 5, at least 5 words. Do you know what it stands for? You forgot. It's difficult, 5 words. It's not that easy. How about you? Do you know? You remember what it stands for? Okay. It stands for light amplified. Keyword is amplified by stimulated. So that's S. A is, let me just capitalize this. Stimulated emission of radiation. Okay, so LASER. So that's laser. It's a made-up word. All right. So there are two light sources that we use in the lab, right? What's the difference? One is brighter and the other is darker, dimmer. Other than the brightness, what else do you observe? So you guys are working in the optics lab, right? No, you are. So you're a team with him, with Clement, right? Why are you separately? You're supposed to be a team. It's all right. So other than the brightness, what else do you notice? Have you turned on the LED source? Yes. I mean, there are two lasers, right? One is red, one is blue. I'm sure you have played with it. But there's also an LED. It's like a flashlight thing, a USB flashlight. Okay. Huh? Yeah. Sorry. No. The real one is a laser, yes. But the LED is a white light LED. Okay. Okay. If you have not played with the LED in your lab, at least you have played with LED flashlight, right? I mean, this is an LED flashlight. Okay. Let me just do a quick demonstration. Aha. Okay. Okay. What is the difference? What's the major difference between this and the laser you use in lab? Yeah. Yes. Directional. Yes, correct. Directionality. Okay. Directionality. So, directionality. Directionality. Okay, or directional. Laser is very directional. It stays as a beam for quite a long time. It can propagate for a long distance and stay directional. All right, unless you use a lens to defocus it, to diverge it. Otherwise, it stays pretty directional. Why is that? What's the main difference between this and that? Coherence, that's a good word, but what does it mean? Yes, because the way they are produced, correct. The reason laser or the photons in the lasers can stay in the same direction and the photons in the LED cannot stay in the same direction, that has to do with how they are produced. Okay, how they are produced, and to discuss that, we need to invoke the concept of coherence. Okay, coherence. Let me just give a quick explanation on the mechanism how light are produced in both devices. Okay, so fundamentally, they're both produced in the same way. There is some kind of, let me just use a coil as, you know, like coil in the light bulb. But of course, this is a dial, a light emitting dial, but it's not really different. It's basically you energize this thing, and once it relaxed back to its natural state, it releases the energy absorbed in the form of radiation, right? So once you energize it, you release radiation. After a while, it releases radiation, and this is called fluorescence. Fluorescence. Yeah, so we learned about fluorescence also in the last lecture when we talk about MV center, correct? Okay, now here is also a diode or whatever light emitting source there is. and you put in current or some form of energy. Even you can use thermal light to energize this thing. It's possible. So some kind of energy input. And then this, after, so first you would be excited, of course, but when it was relaxed, it will be, it will release the energy absorbed in the form of radiations, okay? So fundamentally, they have the same chord, but the difference between the LED and laser is that this is contained in an optical cavity, okay? In an optical cavity. And there, well, in this case, there's no additional structures around it. So there is simply just an opening, and then whatever light that make through this opening gets out. So it's very divergent, yeah? But in this case, we have this cavity, and has anybody seen an optical cavity before? I mean, I'm sure sometimes people read about cavity from whichever source, but has anybody seen a real optical cavity working in life? No?
Those like pairs?
Yes.
Okay.
Yes, but have you seen like laser light bouncing around in it? Okay, so a cavity is a wonderful device. I love it. It's really cool. It's basically a light trap. Light trap. So a cavity are made of mirrors, high reflective mirrors. Mirror 1, mirror 2. Okay, so usually one of the mirror will have very, very high reflectivity, such as maybe like 99.9% reflection. And the other one will have, so let me just say low, and this is high R, high reflectivity, and low reflect. But by low, I don't mean really low, it is still high, like 90. Okay? So every time when, let's just say a photon, every time when a photon arrives at this interface, it bounces back. There's 90% chance that it bounces back. Okay? And then when you arrive here, you definitely bounce back because there's only 0.1% chance it will go through. So what happened is light, when the first photon is emitted, it will circulate inside this cavity almost indefinitely. Okay? That's why it's called a light trap, because photon light is trapped inside. And why do we want to do that? What's the purpose of trapping light inside, at the vicinity of the light source? This has to do with one of the questions you asked last lecture. You asked about bosons and fermions. If you remember, bosons are particles that are like to mimic each other, right? Like they are like sheep. One sheep does this, the other sheep follows. They all move in the same way. They like to move in the same way. They don't like to be different. They like to be the same. So the reason we put a light source here is, the reason we put a cavity here to trap this first photon is because we want to use it to as like a template for subsequent emissions, right? So when this passed through the light, the source for the first time, and if this happens to want to emit, then it will emit a photon that is, if not identical, but it will emit a photon that is very, very similar to whatever this photon had, the property of this photon has. Okay? So in other words, all the emissions, all the fluorescence, due to this bosonic feature due to this bosonic property of photons. They will be stimulated into the same mode. That's what we characterized light or photons by photon states. And this state, we call it mode. Okay? So because of the cavity, the first photon will set up the mode. Whatever that mode is, it will set up the mode. And everyone will, every sequential fluorescence or every sequential emission will emit photon into that mode, so that they all have the same spectrum. They all have the same direction. They all have the same polarization. Everything about photon that one can have, they have the same thing. It is possible to emit. Sometimes it is possible to emit photons that are a little different from this. But this kind of photon will easily leak out. Because the mirror, okay, maybe I should say, the mirror is reflective at 90% and 99%, typically only for a single frequency. For other frequencies, the reflectivity is not that high. Okay, so light trap, for every trap there is a resonance frequency, right? Okay, trap only work for light that is emitted in this resonance, in this frequency, so that it can remain in the trap, and that's why it's called resonator too. But once in a while, there is photon emitted from the source that is at a different frequency, that is different from this photons, and in that case, most likely this will be another frequency, and it will not stay trapped. It will leak out. If it does not stay trapped, then it will not have a chance to get amplified, right? Because it needs to stay there in order to trigger other photon to fall into that same mode. But if it leaks out easily, this the other one harvests on energy much more than this one. Okay. All right. So that's just a little bit about cavity physics. All right. So this cavity facilitate the generation of identical photons. Now, every once in a while, there could be photons leak out from, after a large number of them have been already generated in the cavity, and they keep bouncing and generate more and more. Every once in a while, there's still 10% chance, 10% of the time, photons can leak out, right? So these photons that is generated, that is stimulated and generated into this mode, can leak out from the cavity. And when we collect them, they are in the same, since they are in the same mode, they travel in the same direction. They have the same color, they have the same polarization. Okay, and that is your laser beam. Okay? So that's one distinguishable features we can tell between LED and laser. There's another one, and this one is perhaps not as visible unless you do spatial measurements, and this is called interference. Okay, coherence, or the ability to interfere. Okay. All right. Other than light being emitted in the same mode, there's another thing that is very different between the LED and laser, and it's called coherence, and that is what you talked about earlier. And there are two types of coherence. There are spatial coherence, and there are temporal coherence. Temporal, yeah, I think it's spelled that like that. Spatial and temporal. Okay. So what this means is, if you take this LED light and then you split it with a big beam splitter, right? And then, so this is LED. And then you put them back together with mirrors, with mirror arrangements. Okay? You put them back together with mirrors and another beam splitter. Okay, let me just mark this as mirrors, beam splitter. Okay. And then they can, part of this beam will go through. I'm sorry, I think I used the wrong direction. My bad. It's like this. It should be like this. Let me just mark it with another color. Part of it will go through, and part of this will get reflected, right? So they are first split and then they are combined. Okay. And here you put a camera. Yeah? Here you put a camera. And you watch. What do you expect to see? Well, if this is the camera, you'll probably expect to see from this source. If you block this path, you'll expect to see this source as a blob, right? And if you block this path, you'll expect to see from here another blob. Correct? Okay. And if you open them both, what do you expect to see? A brighter blob. Sorry, bump, not blob. Bump 1, bump 2, bump 1. And together, they are just bump 1 plus bump 2, brighter bump. We can write them as bump 1 plus bump 2 equal to just brighter bump. Yep, okay. That's what you will typically expect to see. Now, with the laser, now we're really talking about spatial coherence. With the laser, you do the same thing. Okay, so let me just put laser here. You do the same thing. Split. Because it's more directional, so I just draw one line. Okay, so 1 and 2. Yep. So for a laser, again, we expect to see one bump when we block one path. So this is LED. This is a laser. Bump 1. And if we block this one, we will see another bump, bump 2. Yeah. Now, if you that through both paths, the magical thing will happen. On top of the bump, you will see fringes like this. Okay. So to describe it, there are 2 bumps, but then you will see fringes, and this fringes is usually in the form of a cosine square. So bright, dark. So a cosine square is bright, dark, bright, dark, bright, dark. 0, 1. Okay. So this is a cosine square. Okay, cosine square. And let me just write as function of x. Okay, bright, dark, bright, dark. And this only happens when you have both bins. Yeah. This is called interference. And here you see there's no interference, right? So experimentally, if you set it up like this, you can clearly see that these 2 light sources are also very different in terms of their spatial coherence. Yeah. And why do I say coherence is equal to the ability to interfere? Because this extra term here, this is also this is an oscillating term, like a AC, yeah, and this is more like a DC. So they are steady. They are like a constant over the screen. Yeah, they don't change. They don't modulate. But this term, called the interference term or the cross term, it oscillates. Okay. And you see the difference between this and this is that the oscillating term is gone. It's different. I'm sorry, not different. It's gone. It disappeared. So in order to describe light in general, we use something called the coherence function to characterize this oscillating term. When the coherence function is 0, right? That means no coherence. So you don't have this interference term, and there's only the DC term. When the coherence function is 1, you have this coherent source, you have this coherent situation, and you have the interference, you have the fringes. Yeah. So last time I told you that coherence is just a make-up word or people invent to indicate as an indicator for the ability to demonstrate the quantum mechanical behavior, right? In this case, it's not a quantum mechanical. These fringes are not due to quantum mechanical behavior, but simply because light is wave, so it will do that. But that's all right. I just want to use this example to introduce you to the concept of coherence and how coherence function is defined. Yes? All right, so coherence function again. Coherence function is an indicator. For what? For the ability to interfere. If this indicator points to 0, you cannot interfere. If this indicator points to 1, you can interfere, right? Is it possible to have anything in between? Yes. This indicator is a continuum. So on one end, you have full coherence. Fully coherent. On the other end, you have incoherent, right? And it's like rainbow. You can have everything in between, here, 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 and here. So that means the amount of coherence that shows here could deviate from 1. And that means if you draw a line across here, right? If you take a line across, you see this. You see a bump. When 2 lines are both present, you see a bump. Now, so this is this corresponding to this. So this is when the coherence function is 0. Now, if the coherence function is 1, you have this oscillation. Very, very bright, very, very clear contrast from bright to dark. 40 dark, bright to dark, bright to dark. Now, if you have the coherence function, not 0. If you have a coherence value of 0.5, what do you expect this to look like? Yeah, it looks like this. Okay, it looks like this. So you can see that this is almost like the intermediate state between these 2 extremes, right? It has a significant part of the DC, but also on top of it has modulation, the AC. Some, but not 0, but anyway. So this is what is between is called partially coherent or partial coherence. Yep. And this fringe can get large or small, or large or small. When it gets large, it becomes like this blue one. When it gets small, it becomes like this black one. Yes? All right, great. Now, so that's one thing about the difference between LED and laser. Okay, there's also temporal coherence. Okay, but that is harder to explain. That's a little harder to explain. And since it's relevant to our experiment, I will try generalized our concept of that spatial coherence that we have, and use it for the time domain. All right, it's kind of hard to explain. All right, let me try this. So earlier I write down this. Correct? Yeah. Now, if I would do a derivation, so instead of just describing what I see, if I want to do this derivation, how should I do this? I have 2 light field, E1 and E2, right, from the 2 arm. So I intensity is, so this is the derivation. Intensity is the module of the electric field, the total electric field. And the total electric field now has 2 components. One from the upper arm, the other from the bottom arm, lower arm. Yep. Now, anybody know how to do this operation? Do you? Yeah. Do you know how to do how to continue this calculation? Direct formulation.
I usually divide them, I think.
Okay. This is a module. So a module means the complex conjugate and the complex part multiply together. That's what module means. Okay, so in order to continue our math, we need to break this into the complex part and the conjugate part. Yeah. I'm sure some of you are familiar with this math I'm doing here. It's not terribly hard, but it could be unfamiliar if you haven't done it a lot. Yes? Yes? Okay. Now, this is, again, just this. Right? Going back to the module form. Okay. But this is interesting. Let's just keep it for now. First of all, I want you to see that this is a cross term. So it has contribution from 1, contribution from 2, right? Every term here is contribution from both. So it's a cross term. It's almost like an interaction thing. So this involves the property of both. Yeah. Okay. I just want you to notice that fact. Okay. And this is just I1 and I2, right? I1, I2. Yes? Okay. Now, what do we do with this? So I want you to notice that when we divide this bin, yeah, sure, it's all right. So this is a bin splitting cube. So you've seen this in your lab, right? So it's like a cube. All right. So it's a bin splitter, and it split a bin into two lines. And we call this E1, and we call this E2, and here's mirror. Okay, mirror. Okay. E1 plus E2. And of course, the other port is also possible. So not forget that, but I'm gonna focus on this one. Okay. Now, if you pay close enough attention, you see that this light travels a longer path. Yes? And this light travels a shorter path. This longer path, in terms of, so we know light field, if we have a single frequency light field, it's described as cosine kx omega t, right? So this phase in the light field, of course, it has an amplitude. The phase in the light field could change as you propagate in time or as you propagate through a certain distance. Okay. Now, when this goes from here to here, other than the time spending is different, the length traveled is also different, right? Okay. So you could easily see that this additional, so for E1, I have this travel length. For E2, I have this travel length, this additional travel length, right? And I'm not gonna go into the detail, but you can imagine that here, the phase, the relative phase between this will be, it's almost like they are the same thing, but with the relative phase difference of k delta x. of a relative phase difference. Yeah. Okay. Now, let's come back to this part. And since we're writing this in complex notations, using a complex notation for the phase is appropriate in this case. Okay, so let me just write. So E1 and E2, let me just rewrite this, and I'm gonna highlight the phase difference between these two. Other than, of course, this represents the entire field, yeah? But we know that this, other than, they have a lot of differences, but most importantly, they have a global phase difference. Yes. And here is a complex conjugate of E2. So yes. Okay. So what I want to say is, you see, this is already pretty close to what we have here. Okay, and let me just skip a few steps and tell you that if we could factor out things appropriately, then we will end up with no, that's just this. Okay, I got myself into a little trouble. Okay. All right. Let me just stay. Yeah, let me just stay like this. All right. So when you factor out things, you have factors and you have the phase. And what is here we define as the coherence function. So at the end, the coherence function would be I understand this might look a little different from what we derive here, but basically, I just want to give you the gist of the derivation. I don't want to get into the technical details. From these arguments, you can see that the interference term can have the factors in front of it, and that factor, however it is defined, control the amount of interference that can be present in your signal, right? And I'm telling you here that if you've gone through all the mathematical step correctly, you end up with this derivation, okay? And people call this autocorrelation. Okay, because it's derived, being 1 and being 2 are derived from the same bin. They're just same bin making a copy of this bin, and then you combine them. Okay, and it's almost like you make a copy of this bin, So this is the original and this is the copy, and you multiply the original and its copy, and then you average them. Okay. All right. The reason I try to go through this very tedious math is because I want to motivate this concept called correlation. And correlation is not it's not a very intuitive concept, but it's very useful in quantum optics measurements, in quantum optics experiments. And correlation function or convolution function, it has many different versions of names, all involve terms like this. Okay, and this whatever is below is just some kind of normalization vector. Okay, this is for normalization. Okay. And it could be very confusing. Yes.
Didn't you call this coherence?
Yes.
That's also the same.
Coherence is in yes, thank you. So coherence is in the context of physics, we'll call it coherence. But in general, mathematically, it is called correlation. So coherence, correlation, convolution are all the same thing. Okay, let me just write it down for you. So coherence is what the term that physicists would use, coherence. Okay, this is for physics. Correlation is more of a mathematical term, but also physicists use a lot. Some of them, not all of them. Most of the people use coherence. Some of them will the specialist who knows what this is will use correlation. So this is like between physicists and mathematics. There's another term called convolution. Okay, that is strictly mathematics. But I want you to know that they all mean the same thing. Okay, and depending on what you put in this function, if you put in the function with two different sources, it's called cross correlation. If you take, okay, sorry. So coherence and correlation, this always involve two inputs. Okay. And if these two inputs are derived from the same source, like in this case, they are derived from the same source, it's called autocorrelation. It's like making a copy of yourself and correlate yourself with yourself. Okay? Correlate Wayne with Wayne. Yeah? So in that case, it's called autocorrelation. But if we have two different sources, like truly different sources, like for example, laser, you have a laser and you have another laser, laser A, laser B, and you take the two bin and you try to put it into an interferometer. You try to just combine them like this. It's called cross correlation. Okay? Yeah. So these terms could be super confusing, and I'm trying to do the best I can to motivate them in a logical way, and make the concept as understandable as possible. All right. So after going through all this math, all I want to do is just tell you that this term have a physical origin. Okay, it has a physical origin, and this form of measurement can be generalized. You can put in anything in between. So this is intensity, this is field. You can put in intensity, or you can put in intensity square. You can put in intensity cube, whatever. Anything that you want, you can put into these two spots, and integrate them. So average means integration. Integrate them, and then and that will be your correlation, whatever correlation that corresponds to. Okay. All right. So since we have motivated this form, I want to approach it from. Yeah. Okay. I want to approach it. Thank you. I want to approach it from another angle. I want to maybe spend a little time on mathematics and tell you why that form is special. Okay? Why that form turns out to be very special. Why is it useful? I mean, yeah, we kind of motivate it, but why does it happen to be useful? Not everything that we cook up is useful. So why is that useful? Yeah? Okay? So I have a note. You don't see me do this very much, but this is one of the few times I will have a sheet with me. Okay, so correlation. So correlation basically. So if I have a correlation function, that basically means A times B average. Yeah, A times B average, and I want to motivate this discussion from a measurement point of view. From a measurement point of view, it is mathematics, but I want to stay close to physics as much as possible. Correlation means pattern recognition. Yes, pattern recognition. Yeah. So in your quantum optics, lab, you have two detectors, right? And you try to send two beams to them. However, you get these two beams, either by splitting a beam or by some kind of special photon source. Okay, so you somehow you manage to get two beams, and then you send them to two separate detectors. Yeah, A and B. Okay. Now, what we want to do here is we want to evaluate if there is any. So the motivation in your experiment is to see if there are photons in your beam, right? And if there are photons in your beam, you are probably going to expect a pattern like this: boom, 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 boom. If this is your signal, and this is your kind of measurement time, right? So this corresponds to this beam with little balls called photons, right? So this is the pattern that you will expect from your signal if there are photons, right? So how do we know if they are there, if the photons are there? That's why we want to do some kind of pattern recognition measurement. Yeah. Okay. So let me go back to the math. Having motivated this already with your physics measurement, let me go back to math. If you have a pattern, so this is called signal A. Signal A, okay? If you have a pattern that looks like this, boom, 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 okay? Let me extend this a little bit more, longer, boom. Okay, and the time between this dip and this peak is 2t, and this is t, this is t, this is t. Okay, and say this is time 0. So if you have a detector and the detector has some kind of pattern in it, boom, 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 like this, dip, pick, 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 dip. Now, if you make a copy of this, right? Either a full copy or a partial copy, and you're allowed to change signs. Okay, you're allowed to flip a dip into a pick and a pick into a dip. Yeah. So say you're allowed to do this. You make a copy, or you take this signal and you make a copy. And in copying this, maybe you lose some of the bumps. Maybe you skip one, miss a few of them, or maybe you get the sign wrong. It doesn't matter. So say you have make a copy and then you get this pattern. Okay, and the difference is this. And your time 0 gets shifted to here. Are they very different? Well, it seems to be. It seems to be very different. However, despite the differences, they still have similarities, right? Some of the patterns survived. For example, this T interval survives, right? And this could be that, and this could be this, or this could be just this flip, right? We don't know what this corresponds to, but it does have some. Despite all the differences, it does still keep some of the patterns. Yes? Okay. Now, if we do another copy, oh, by the way, so when this is not guaranteed to be the same height, and this level is not guaranteed to be the same level. So if this is A0, this could be B0, right? And the height could be different, right? So I'm just saying that in the process of beam splitting, there could be a lot of things that are lost. There could be a lot of things that are changed. But nevertheless, when you make a copy, some of the pattern, if there is a pattern, it will remain. Yeah? If there's a pattern, it will remain. And let me just make a few of them, and then we will inspect them. After that, we'll take a little break. So signal D, signal C. How is signal C different from signal A, from the original signal? Besides the time 0 is, oh, sorry. I want to shift the time 0 to here. Besides the time 0 is different. How is that similar to this? We see that there are two peaks that are separated by 2t, right? And that corresponds to this feature. Yeah? And then we have another t that corresponds to this feature. And then we have another 2t, we have a dip that corresponds to this feature. So basically that copies this, and that. And it skipped this one. Other than the shift. Okay. Okay, maybe signal D, A, B, C, D is the last one I will put here. Okay. Signal D obviously copies these 3 peaks. Yep. All right. Great. Good. Awesome. Now, according to the formula we were given, correlation equal to 2 inputs. Okay. Signal A, and let me just call it signal X. Average, right? Average means average in time means integration. Because this signal is a function of time, right? Each signal is a function of time. Okay, let me just write it down like this. The signal is a function of time, so you integrate, right? Okay. There's one more thing I did not tell you. With every correlation, we have a parameter, a delay parameter. Okay, that means when we make a copy, we delay it by a certain amount, by tau. Okay, so this delay could be 0. So when we make a copy, the delay could be 0. Or the delay could, like in this case, for example, you see, the time 0 is shifted, right? So it seems like I copy some of the features, but it's delayed. So it was this 2 feature, maybe this 2 was supposed to be pretty far away from time 0. Now I shift it forward. Okay, so I make a delay. Yeah. Okay. So after integration, this thing is a function of tau. Tau determine the integral. Time will affect the integral value. Yes. Okay. So let's see what happened if we do with this. Okay. So if we have signal A and B, and this is the correlation of the function of delay. This delay. At each delay that we try to move this, we have a value. Yes. Now, so time 0 match time 0 here. So you could almost draw this one as here. Almost like this. Yes? So if I just match the time 0 with 0 delay, the 2 signal with 0 delay, you have a value like this. They will line up like this. Correct? Now, if I multiply them, what will happen? Let me before I multiply them, just for the sake of convenience, let me change my scale. Let me offset signal B by this amount. Okay, so that this is 0. And this is whatever value it is. So if this is, for example, if this is A and this is B, okay, when this value here will be B minus B0 minus A, and this will be B0 plus lowercase b, right? If I shift the thing to this level and call this 0, then this will be minus A, and this will be positive B. Okay, correct? Okay, so let me just, for the sake of this calculation, let me before I multiply them, let me just offset these functions by a certain amount, and call this -1 and this +1. Okay, and this is +1, this is +1, this is +1, this is -1, this is -1. The rest is 0. Yes? Okay. So the point I want to make is when I have them lined up with 0 delay, without shifting this signal with 0 delay, then this will, when I multiply them, this will multiply to a 0. 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 This will multiply to 0, 0, to 0, to 0. Correct? So overall, I have 0 when I integrate everything, because everything is 0. I'll have 0. So this is 0. Now, if I shift them slightly, what would be the product? Still 0, right? If I shift them just slightly, like from here to here, this still line up with 0 here. This still line up with 0 here, right? And the rest will also line up with 0 here. So this will still be 0. Now, if I shift this by enough amount, so say like here, so that this align with this, I get slightly more interesting result. Yes? So this -1, +1, this will line up with this peak, and this will line up with this peak, right? -1, +1, this is minus. This give you -1, and this give you, this give you +1. Okay. So here I have -1 +1, still 0. Okay. So that is if I move this thing to here. Now if I do it further, I move it to here, so that this and this peak and this are aligned, and this peak and this are aligned. Yeah. And since this is P apart, they will definitely match. When one peak is aligned, the other will match. Okay. So in this case, what do I get? Here I have a -1 multiplied by +1. I have a plus -1. Here I have a +1 multiplied by -1, right? I have a -1. Finally, a non-zero value. Okay, non-zero value. And as you can imagine, if I move to other values, it will remain 0, 0, 0, 0, 0, 0. Okay, so the rest is 0. All of them are 0. If I move this to here, matching this peak, right? Matching this peak with this peak, I get +1. But at that time, this will multiply to a 0, so this will be 0. So that gives you a +1. I give you this. Okay, so by the way, this is 0 delay. Yes, you understand what I'm doing here? Okay, so what I'm trying to say is, when I do a correlation measurement, is to take two signals and shift one with respect to another by a certain amount. And after you shift them, you multiply the entire signal and you sum over. Okay? you sum over, and you see the net contribution. Yep. And if you have a net contribution, either positive or negative, that indicate there is correlation between the two signals. Yeah, when you have a non-zero value, that indicates you have. So let me just put this here. Like, yeah, we have a positive correlation. We have a negative correlation. When there are non-zero correlation value between the two signals, that means when correlation exists. So when correlation is equal to is non-zero, that means there exists pattern, similar pattern between the two. Yes, there exists similar pattern between the two inputs. Now, since these are in case of autocorrelation, this one is the copy of one is strictly the copy of the other, right? So I can easily make up a signal D, signal E, and signal E will just simply will look like this, with 2 T, 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 but a time shift. So other than the time shift, everything is the same. Okay, so this is called autocorrelation. Auto means itself. You make a copy that is strictly itself. Okay. And you do this correlation measurement. And when you see non-zero values, that means there are similar pattern between the two inputs. Okay. Now the funny thing is, if there's no pattern to begin with, there cannot be similar pattern, right? If you only have noise, right? If you only have noise, or zero basically, so noise means zero. If you have only noise, if there's no pattern to start with, there cannot be any correlation, right? So a non-zero correlation implies similar pattern between the two inputs. And when there is similar pattern between the two inputs, and the two inputs are actually the same, from the same copy from the same source, then this must imply that there is a pattern. So in terms of auto correlation, so this must imply a pattern exists in the original signal. Okay? Yes? All right. So I won't go through this, but you can play this game yourself. We're gonna have a 5-minute break, and if you're not tired enough, you can try to mentally do the multiplication between signal C and signal A, and then see what the correlation function will look like between this and this. And surely you will find that there will be non-zero point at certain delays. Yeah, because part of the patterns are copied to here. So when you delay this by an appropriate amount, they will line up, and they will give you a non-zero result, right? So the same thing will work here too. So I'm writing it down just to give you examples so you can play with and get more understanding of this, all right? So that's correlation measurement. And let's take a 5-minute break from here, and we'll come back to this. Yep. Get some water. It's okay. Just leave it.
Can I ask something?
Yeah, sure. If you're not tired.
I am, but I'm also curious. You know about this picture here. Like, I have a question which been like bothering me for like
Centuries.
quite some time, and not a century, but like
If you're a vampire.
when is light quantized, or like which light is quantized, and like because I'm writing a report on the first lab,
Right.
and then this question came up.
Yes.
And it's also come up in my quantum course this summer, and also here again, you know, like I wonder why does it look like this here and not here, you know? So I mean, because this shows quantum properties.
No, actually, no.
No?
For light, in the case of light, the fringe does not mean quantum property, because remember I said the quantum nature of light shows in its particle aspect.
Oh yeah.
And
right,
interference fringes belongs to the wave aspect.
Yeah, that's right.
Yeah. So seeing interference fringes does not mean light is quantized. Actually, this coherence here that I introduced, motivated by the fringes here, in the case of light, it's called optical coherence.
Oh, okay, I get it.
But in matter wave, it's called quantum coherence.
Yeah. Why are
depending
these,
on the context?
Why doesn't this show the fringes though?
That's a deep question. You're asking the right question. Let me put it this way. Actually, it can.
Okay.
But only within a very small amount of time.
Huh.
And that has to do with temporal coherence. So only when two, the spatial and the temporal, only when two conditions are in place, then you can see interference fringes.
Yeah.
As a matter of fact, if you remember, if you were curious and you gone through your menus, you'll see one of the additional lab. No, actually, one of the alignments that asks you to use LED light, the interference fringes from the LED light to align your interferometer. Yeah. So in that case, there is indeed, you can indeed see interference fringes from LED light, but only when you displace the beam small enough. It's quite technical, and I think it would take some time for me to explain it. But I want to give you the gist is basically, so in terms of optical interference.
Yeah, I mean, because if you draw, I mean, this one looks like this, right? Or something like it.
Right.
And this one is just
a constant.
One bump.
This is this on top of. So this is this. This is this.
Yeah.
And this is basically this modulated.
Okay.
So what happened here is the intensity that were distributed evenly before, in the case of incoherent light. Now the intensity here moved, is gone, right? Where does it go? And well, energy has to conserve. Where does it go? Well, it goes to here and here. So intensity gets concentrated to certain areas.
Yeah.
And in other areas, it is strictly zero.
Yeah.
And so, okay. So this belongs to the wave. So this belongs to the wave nature. Okay. And since light is intrinsically a wave, classically it is a wave. It doesn't matter if it's a LED light or a laser light. It must be able to do this. The question is, how easy it is for you to see it. For LED light, you have to make the beam path match.
Yeah.
Almost make the beam path identical between the two arms.
Yeah.
In order to see this.
Yeah.
But for LED light, for laser light, you don't. There's much bigger tolerance on that, and that has to do with the temporal envelope.
Does it just have to do with the phases? Because like sometimes it is inference, and sometimes it's the opposite. I don't know the word.
Correlated?
No, you know, it's destructive and
destructive and constructive interference.
constructive interference.
Well, if you can do destructive or constructive interference, that means you have this.
Okay.
The case of incoherent means you cannot even do that.
Yeah. And this one isn't incoherent at all.
Yeah, that's incoherent. That's not coherent at all. That's incoherent. That's the extreme. That's this. Yeah. And when I was explaining there, I don't want to get into this yet. I don't want to tell you that it is still possible for it to interfere. Okay, I just give you the zero order answer. Okay, but the first order answer is the LED light does have all the coherence are a continuous value. It is, yes, there could be zero. There could be occasion that both spatial and temporal are both zero, but most likely they have some value, some finite value, even though they are small, right? And those coherence can still be shown with appropriate arrangements. They can still be shown. But that is just the optical coherence. And fundamentally, if you like, and I think of it in this picture, fundamentally they are all photon wave functions. But some photon wave function has a bigger envelope, longer time envelope. And some photon function have a shorter time envelope.
Oh, yeah.
Okay? Yeah. And when you have a shorter time envelope, okay, so one arm has this and the other arm has this, right? They are displaced. There are some time differences between the two. Then you must match them in order to interfere them in space. Otherwise, they are just one photon arrived, they give a pattern, and the other arrived at a later time. They give another pattern, and the two doesn't even meet. It doesn't even make sense for them to interfere because they are not in the same space at the same time. Yeah. Okay, so that's why. So in order to understand how come fringes can still come out from an incoherent light, you must understand temporal coherence. Yeah. And temporal coherence, and I like to understand temporal and spatial coherence just as the width in time or width in space for the photons. Yeah. So the size of the photon wave packet, I like to think it that way.
Yeah. It's just a matter of whether their faces match or meet.
No, the envelope. The faces is this, the oscillation. The oscillation has certain phases.
Okay, sir, but can't you say that this has a phase as well?
Yes, they always have phase. They always have phase.
But I mean this. Okay, I just mean that they are in different places in time.
Right.
Yeah.
If they are in different places in time, they cannot even. I mean, interfere means both need to be at the same place, right? If they are in, you get it? Yeah. So anyway, maybe I'll be able to come to that point. We're going rather slow with this. We're here, we're almost finishing this. I don't think I could do this within 90 minutes.
All right. Yeah, we'll see if this lecture actually turns out shorter.
Well, my primary goal today is to make it short, even at the cost of not finishing it. All right. All right, I hope everybody has some water. Okay. All right. I do want to finish the math here, though. I don't expect you to fully understand what's going on here, but I just want you to at least not be afraid of it, okay? Correlation is not a familiar concept to many of us. And I hope through this motivations, you'll not appear as scary as it once was to you if this is not your first time hear about this term. Okay. Now I want to finish this just with a little remark. So earlier I said correlation is this signal and this signal, A signal and B signal. And if you delay the B signal by a certain amount, right? And you multiply them. Okay? dt. Okay. Now, remember earlier I said, I would like to offset this to 0 and then just have the signal as positive and negative, right? So this step is sent as this. Yes, I separate the fluctuating part. Plus, minus, from an average part. Okay. The average could be, just the noise level of your detector. Same with the signal B. All right? Yep. Now, okay. So if I continue, so all this that we said here is very qualitative. It's quite qualitative. And now I want to put it in a more quantitative foot, so you can understand what is written on the menu. Yes. Now, so if I multiply this, if I break this brackets, then I have yes. Good. Now, this is the game we were playing earlier, right? So we take the fluctuating part, the plus 1, minus 1. So this is plus 1, minus 1, this is plus 1, minus 1 at different time. And then we multiply them, and then we have, like from this segment, we have this contribution. From that segment, we have this contribution. And we sum them all up, right? And the result, the summing, give us the correlation, right? Well, when I was doing this, I completely ignored what happened to the DC part. Yes? I completely ignored this part, this A and this B, 0. Okay, so here they are. Okay, and I just want to show you what happens to them here. Okay. So let me say that this term so let me minus. So if the integration time is from capital minus capital half capital T and plus capital T plus half capital T, then the first term, the integration of the first term will be A naught times B naught times T, correct? What about the second term? What do you think? Well, the second term is just the pattern itself integrated, right? Most of the times you have fluctuations. I mean, most of the time the pattern goes like up and down, up and down, up and down. It does have pattern, but the value goes up and down, up and down, up and down. So most likely this will average to 0 because you have 2 up, 3 down, 2 down, 3 up, 2 down, right? If I extend this, you have more of this, and overall you most likely have the same amount of up and the same amount of down, right? So this will give you 0. And A, this will also give you 0, right? And then we have this. And this is the term we were playing with earlier, right? So let's keep it. Yes? Okay. Now, so when I do an average, right? When I do an average, it's basically integration and divided by the total amount of time, right? So an average means divided by the total amount of time. Okay, total amount of time. So that gives you. So anyway, these are gone. But here you have the t cancel each other. Yes. All right, and here of course you have this. Okay, so what does what was the outcome? What's the outcome is, oh, by the way, this is 4. So let me write it down here again. Let's start with this. Yeah. So my last line is okay. So that's just the copy of my last line, right? And this has the same form as this, right? Yeah. So this is basically just yes. Okay. So what does this mean? This means the correlation between two signals is equal to a constant, which is its offset. Okay, a constant times its fluctuation. Yes, right? So really the correlation is in the fluctuation. It's not, it has nothing to do with the constant, the offset. The offset is immaterial in this case. Okay? And typically, we like to normalize because this value could be large or small, and that could affect your correlation value, right? So, and since the offset doesn't really has any physical meaning to it, we like to eliminate it. We like to normalize it by simply. So let's redefine this as yes. Okay. All right. Okay. What does this mean? All right. So this is the final form that you will see on the textbook. What does this mean? Interesting thing is, here's a value of 1, right? Here's a value of 1. And so if you have negative correlation, if you turn out to have negative correlation, yeah, because this is always a positive value, correct? We derive this from the, I mean, it's always a positive value because the signal is positive. It's an offset, it's a signal offset. So it's always a positive value. So depending on your correlation, if you have positive correlation, you have a correlation value larger than 1. Okay, so 1. If you have 0 correlation, you have a constant 1. Yes? And if you have positive correlation for certain delays, then then you look like this. Yes? And if you have negative correlation, you look like this. It all suppose that correlation only happens within a certain window, within a certain delay window, you will always look like this. At the long time limit, it is most likely 0 for physical case. For the long time limit, for the long time delay, they are uncorrelated. Okay, so they fall back to 0, to 1. Okay. So this is the figure that you will see often, and this is the figure you see in your lab menu and your measurement. What is special is this thing called 1. So what does 1 mean? In this case, 1 means uncorrelated. Uncorrelated, okay? Not 0, but 1, okay? Uncorrelated means 0 correlation in the fluctuation. But as for the total signal, uncorrelated means the total signal, the signal, the correlation for the total signal is 1. Okay, just note the difference. Okay. All right. And of course, these are normalizing factors. These are normalization, right? Because I say I don't want this value to fluctuate. I don't want it to fluctuate so much with different experiment I do. I do want to have the same standard. So I normalized my measurement to the light intensity that I have, or the detector efficiency that I have for each experiment. So the offset, whatever that is, I normalize it away. So I have a standard value of 1, that which indicate uncorrelation. And so this is all the physical parameters are here. All right. So I want to bring your attention back to this. So earlier I told you that this is the first order coherence function, right? The first order coherence function now is defined as 2 inputs. When you take the bin and you split them into two copies, all right, you do this correlation, and then you normalize to the individual intensity. Okay, so that's this. This is the same. This is the same as this, right? And what is this? This is just the intensity square root. The intensity square root. Okay? And the intensity, the intensity is basically just this flat line, this offset of your detector 1, detector 1, detector 2. You have this offset, intensity 1, intensity 2. Okay? And on top of that, you have the modulation or the fluctuation. All right. Oh, good. Oh, good. So this is a very difficult mathematical tool to use. It's not very intuitive. Okay.
In the manual, we use the second correlation.
Yes.
And I was just wondering, like, isn't that the correlation function as well? Or
yeah, the second.
I'm confused with this one here.
Yes. So that's a great question. So what is the second correlation? In the menu, you have a second order correlation, right? Or the second order coherence. Remember, correlation, coherence, and convolution are all the same thing. Okay, so what does second order, first order means? All right. I think now we're ready to talk about that. Okay, so this correlation concept is general. Okay, this is a general correlation concept. Okay, and here you might notice that I don't call this C, I call it gamma 1, right? The reason I call it gamma 1 is because I want to indicate this as the first order correlation. Okay, and what do I mean by first order correlation? By first order correlation, I mean the input, the signal that I put in, the signal I try to find correlation with, is the field. If the signal is the field, is the first order correlation. If the signal is the intensity, it's the second order correlation. Why? That for a very funny reason, because it is E squared. That's all that to it. So who can guess what would a third order correlation correspond to? E cube. E cube, not temporal. E cube. So if I have E cube, this will be a third order correlation. If I have E to the 4th power as the 2 input in my correlation function, this will be the 4th order correlation. Okay? Okay, so these are called, so this first order, other than the first and the second order, the rest is called the higher order coherence. Okay, and they have their places, but we do not use them. We typically do not use them, so we don't talk about them as much. Okay. All right. So now you understand. That is the general formula for correlation, and depending on what you put in, if you put in the field, that's the first order correlation. If you put in the field square, which is the intensity, that's the second order correlation. Okay, that's how the name come about. Second, first order. Okay. All right. So we have finished autocorrelation. Okay, great. We're not quite done with the optical coherence yet, because if you remember the previous writing I have, coherence, there are two types of coherence, spatial and temporal, right? And the reason we have gone through all this math is because we want to talk about temporal. Okay, so let's talk about temporal. But now, when we are done with temporal coherence, I think, we run out of time, so I won't be able to cover the rest. I'll try to do that other time. But I want to save you enough time to do your experiment. Okay. Let me see. Okay. All right. Fundamentally, temporal coherence has to do with the photon wave packet size. Okay, let me try to give you a more intuitive physical picture. Spatial coherence and temporal. I want you to think of every photon as a wave packet, okay? A wave packet. And that wave packet has its spatial extent, and it has its temporal length, okay? So x, it has its spatial extent. And t, it also has its temporal width, okay? That's for every photon. You won't be too wrong to it's not 100% accurate, but it's not too wrong to use this picture. Okay, so it's from the experimentalist point of view, it is still pretty useful and justified. Okay, so I encourage you to adhere to, adopt to this picture. Now, what justified this width? When we see a laser beam, right, it has a certain beam size. Yes, that size is this wave packet. That's your spot size. That is your photon spot size. Your photon wave function is that big that this photon can appear anywhere. With each measurement, if you can measure one photon, right? With each measurement, you measure one photon that which will appear either here or 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 here. If you have that kind of resolution, spatial resolution, and you make a histogram, you'll find that you collect your photon most likely in the center like this, and the rest is less frequent. Okay, so that's the probability weight packet spatial and the spatial extent is your photon length, and we call it transverse coherence length. Okay, transverse means it's perpendicular to the direction of propagation. Okay, transverse coherence length. Okay, and in time, your photon will. So that picture that we draw is not completely wrong. Okay, you just need to put a little more detail to it. Okay, And one of the detail is that it has a temporal extent. And sometimes this is large. Sometimes this is small. Okay? And what does this mean? That means when I detect, when I have a detector here, right? And I say, and that there be only one photon in my beam, okay? My detection signal, if I can make many measurements at different times, and I make a histogram, okay, I will see nothing, and then something, and then a lot. Sorry. And then nothing. Okay? The likelihood of detecting a photon is peaked at a certain time point. And when you are away from that time point, it's less likely you can detect that photon. Yes? Okay. So say if you have enough temporal resolution, you can detect a single photon. It'll look like this. This is the histogram or the probability distribution in time. And that width is this width. Okay? And this width could be large, could be small, depending on your light source. But basically, every photon has this spatial width, have this temporal width. And the spatial width is called the coherence length. The temporal width is called the coherence time. Okay? So spatial width is called coherence length. Length means length in space. Temporal width is coherence time. Okay? Yep. All right. So let's come back to our discussion on LED and laser. LED versus laser. Okay, now we know the directionality is quite different. One is you're able to focus this to a very good small divergence. The LED you cannot. Okay. The other is spatial coherence that we talked about. And another one is temporal coherence. Okay, so what does temporal coherence mean for both? This means if I send, by the way, this arrangement is called interferometer. Okay, interferometer. The most common one that you've seen is Michelson interferometer. Michelson interferometer involve one beam splitter and two mirrors. This type have two mirrors and two beam splitter, right? So they are quite symmetrical, if you like. This is called Mach-Zehnder. Mach-Zehnder. Mach-Zehnder? Anyway. Okay, so it's called Mach-Zehnder interferometer. Okay, the name doesn't really matter. So as long as you know this is interferometer. Okay. Laser photon has a long coherence time, quite long. And LED photons have short coherence time, very short. Okay, so when you split the wave packet, okay, I'm kind of careful with my my words here, because we know that single photon cannot be split, right? So I'm quite careful. I'm trying to be very cautious of my words here. But let's say we can split it, okay? Super precisionly. Okay, when we split it, there will be introduced a delay, right? Between these two wave packet in time, because this travel a longer path. This also travel a longer path, okay? So when they are here, in one line, so this is, if I call this 1, this is 2, 1 and 2, there will be a lag, okay? And the same with this. Okay. There will also be a lag, right? But now the difference, you can clearly see the difference in the coherence length. Oh, by the way, LED has a short spatial coherence length. So for LED is short, laser is long. The overall difference is LED is short on coherence. Okay, all of it. Short coherence length, short coherence time. And laser is long coherence length, long coherence time. Okay, long. Okay. LED cannot be, let me use a slightly technical term, cannot be collimated. Collimated means, small divergence, very good directionality. LED light, whatever you do with lenses, however hard you try, you just cannot achieve a good collimation. It will just diverge as after some time, after propagating for some distance. But laser, it is possible to achieve good, very good collimation. Okay, so good collimation means very directional. Bad collimation means spread out. All right, coming back to this. So laser has long coherence time. So in terms of when there is a delay present, the two wave packets can still overlap. Yes? And when the two wave packet overlap, you can have interference between the two beams in the areas when they are overlapped. Okay? So that means that fringe that you see, okay? Yes? If you just use visibility, so visibility is defined as the intensity difference over the intensity sum, okay? So try to grab the highest point, the brightest point, and the darkest point as two intensity, and then you subtract them, the contrast, and you divide it by the sum. So it's kind of normalization. So that's called visibility. So when visibility is 0, there's no fringes. When visibility is high or 1, there's fringes. Okay. So in terms of visibility, the visibility will only appear. So if this is, let me say, 1 millisecond, okay, then visibility will be 0, because here the other photon has not arrived, the other wave packet has not arrived yet. And then up, and then down. It'll be like this. When you have the maximum overlap, visibility is the maximum. Okay? So your visibility will, so your fringe will appear for a while and then you disappear. Yes? So that's laser. Okay? So this is time. For LED, how about that? For LED, is there any overlap? No. If there's no overlap, there's no interference. So you will stay 0. Okay? However, stay 0. However, if you can manage to configure your interferometer so that the path is the same, okay? For example, if instead of putting a beam splitter here, you put a beam splitter here, and you put a mirror here, yes? So that this will travel by that distance, and this one will travel this distance. They travel the same amount, okay? Then, in this case, they can be overlapped. Yes? They can be overlapped. And by the way, this is typically a very small window, maybe like 1 nanosecond. It can be overlapped, and then for a very short time, 1 nanosecond, the interference fringes can appear, and then it's gone. Okay? Yes? All right. So the take-home message is coherence is a continuous spectrum. Coherence has a continuous spectrum. It's a continuous scale from 0 to 1. Yeah? The coherence length and the coherence time quantify coherence. The ability to interference in space, the ability to interfere in time. And of course, if they don't meet, they don't interfere. Duh, right? So, so the difference between laser and LED is not qualitative, it's quantitative. You understand that? Because fundamentally, they are all photons. Yes? They are produced by spontaneous emission. Okay? Laser through the work of, through the, by the merit of cavity, the photon can be put into the same mode. So it has like better this and that. It has improved performance. Let's put it that way. It has improved performance. But that improved performance is quantitative, not qualitative. Yes? So they are different. So it's not like one is 1 and the other is 0. It's more like one is 0.2 and the other is 0.7. Yeah? Laser is like 0. So this is like 0.2, and laser is like 0.8. So they are quantitatively different, not qualitatively different. Yes? Okay. All right, so this is great. And this tells us the difference between laser and LED. All right. We have not touched. And by the way, all this coherence that I'm talking about right now is optical coherence. It has nothing to do with quantum. The quantum nature of light has nothing to do with quantum nature of light. Because I told you last time, for pure energy, what's the quantum aspect? For pure energy, the particle nature is the quantum aspect, right? Or let me rephrase it. The quantum phase of pure energy is particle. And the classical phase for pure energy is wave, right? Okay, so all these things I'm talking about, the interference, coherence, interference, and all that, are all pertains to the wave nature of things. And since light is fundamentally classically a wave, it certainly will have ability to interfere. Just the amount, just quantitative difference between different sources. You certainly have, right? Okay. The quantum nature, the quantum coherence, the quantum nature of light is in the particle, as is in the particle phase. It's in the form of the particle, okay? I don't know what's the better word for it. And there we should be able to distinguish between so there we have the so-called classical light and non-classical light. And we will explain what these are in a later lecture. But the quantum coherence will make the qualitative difference between classical light and non-classical light. The optical coherence is only quantitative. It's only a quantitative difference between different sources. Okay. All right. I think enough said today, and let's do a quick quiz. Okay. Let's do a quick quiz, and then we're done. Two questions as before. Quiz, our favorite time. Quiz number 1. Is it possible for LED light to produce interference fringes? Okay, it's pretty simple. Yes and no. There are only two answers. Okay. Okay, please stand up and pick your answer. Okay, let's see. Oh, I like it. We have a lone wolf, a maverick standing right here. You against everyone. Awesome. I like it. Okay. Let me see. I will have. Who's the brave? I'll have someone debate with you. Who's the brave? You try to look away with your bananas. You try to look away. Don't pick me. Don't pick me. All right, I won't pick you. How about you? You two will have a little debate, and then you will try to convince him why LED is not a light, or is not able to produce interference fringes.
Like I will but at the beginning of the lesson, he showed us those rules. He said that with laser you can see those lines from the unit square. But then we confused me into it. But still, I believe what we said in the first, because then I wasn't so concentrated.
So what I heard is if we design an interferometer in a way that two light paths travel the same distance, the LED would exhibit a short time period of interference, but very short. It's because even though the LED light has a very short coherence time, because we designed the interferometer in a way that both paths travel the same, so it would arrive at the destination at the same time, and so the two coherence time would like bump into each other, and so it would interfere with each other. But I also have a question: is that okay if we design the interferometer in a way that it travels the same distance, but what if we use a laser source? Will it like still exhibit the interference in the results?
If they overlap, yes, of course.
And was that only a special case for one photon?
What?
And was that only for that special case when you have just one photon?
When it interferes.
Yeah. Like, I remember some chart that it was like, and it was for the, that was about the LEDs with one photon. If they have same
distance, right?
Yeah.
I'm not sure. Wait, what are you talking about?
Are you convinced that the answer is yes or not? Just tell me, are you convinced after this little short debate?
I don't know.
If you're not sure or you don't think so, just say so. It's okay.
Like, I wasn't sure even before the website started, and now, like, I don't know, like, everybody is there, so they're probably right.
Anybody volunteer to give a second round? Anyone?
I can't do it better.
You cannot do better? Okay. Okay. Okay, you try. Give it a try.
What I know about it is we got coherent line and the coherent for the light itself. And in the region of the coherent light, and that we can do it and we can mix it and make the whole coherent. Then it can be there, but the interaction for the interference is good or not is probably according to its correlation function. The correlation function we got. So I was just that we if the time correlation time for coherence we are in the coherent time and we will get coherence and the strength or the interference good or not is depends on its correlation. Yeah, so it could be coherent, but it will be weak. So we will ignore it, or it will be strong like a laser, probably without it. So LED seems like weak, and we will might just ignore its interference in normal case, maybe I should. So I was thinking it still has coherence, but it's not so strong. So
All right, hands up. Okay, so I want to do it one more time. So now after these 2 rounds of debate, fierce debate, let's pick again your answer. If you now are less sure of, see if you're now less sure of your original answer or you're more sure of your answer. Anyway, pick your answer now. Are you convinced?
Like,
Are you
well,
rather not be wrong than not knowing how why?
yeah.
Going in front of her. So you're convinced LED light can produce interference fringes.
Yeah.
You don't want to be the genius among the
No,
pool. You might be right.
yeah, I might, but I don't know why. So I'm standing here.
You don't know why? No.
Can I try a short,
Yeah,
short
sure.
explanation?
Yes, yes.
Like, I'm not completely sure if it's right, but like,
You have 1 minute.
okay. Ooh, but I mean, so if we have 2 waves, I mean, like, both LED and laser is both waves, right? So like, why wouldn't both be able to interfere with each other? So I think like the difference is basically that the laser has more patterns, and patterns means that the waves will have an easier time to like match. So I mean, if this distance is the same, it won't matter that they're not exactly at the right place, because you will be able to shift it so that they do interfere. But with the LED light, there is no pattern. So the statistical, what do you say? The chance that these will meet and interfere is just very small, but it's still possible. Like, why would the reason be that these 2 couldn't meet?
Okay, great.
It's like if Putin and I would get married. Like, it's so
Putin and who?
so Putin and me.
Oh,
Like,
okay.
like there is no logical explanation why we couldn't. But
Okay.
we can.
All right.
But the probability is extremely low.
Okay, I see. I like that analogy. I like the analogy between Putin and you. Love it. Thank you very much. You can have your seat back. Please sit back. The answer is yes, it can. It's possible. And I love all this attempt that you guys try to justify your answer, because in this process you are thinking. And as I said in the very first class, to learn quantum mechanics, you have to struggle, because it's conceptually so distinct from everything that we have experienced. So in order to really understand what it's about, even just to know what the vocabulary means, it takes a lot of struggling. Even for me, it takes me years of struggling to start to get a little understanding of the subject. All right, so if you're struggling, that's good. That means you are in the journey of getting to know quantum mechanics. Okay. Reason yes, and I will just provide a very simple argument. If you have 2 beams, right, and this is the camera, and this is the chip, right, the camera chip. This is the camera, and this is the camera chip. Okay, and then this so whatever is here give you an image, right? Now, remember in the interferometer we have mirrors, we have like beam splitters, right? So it is very possible that the 2 arms of beams, even they are transmitted and one reflected, the output is the same. there is a possibility that one will land here and the other will land here. Correct? They are specially separated. For a laser beam, if you have this misalignment, they are specially separated. Do you use interference? For laser beam? No, you don't. Because they are just they are not meeting at the same place, so they cannot interfere. Yes? So if they are spatially separated due to the finite length, the finite size of the laser beam, it is possible to have them spatially separated so that they don't meet in space. Thus, there's no interference. In the same way, temporally, they also have a finite width. And if they don't meet in time, they cannot interfere too. Okay? So this is the same. So the temporal alignment and the spatial alignment issue has to be taken care of for both LED light and laser light. The difference is only that for LED light, it is harder to do the alignment. There's less tolerance for misalignment because you have to do the alignment so perfectly that they are 100% overlapped. This is almost 100% overlap in order to get interference to work. But for laser light, because the width is so big, the width is so big, you know, the width is so big, the coherence width, the coherence time is so big that even there is slight misalignment, it's okay. You still have significant overlap, and that overlap is enough to produce fringes in your pattern, in your intensity profile. Okay. Yes. So it's a quad. Again, it's the difference between them is a quantitative difference. Okay. This is a harder one. Given that laser light can produce, I mean, we are all sure that this is a valid statement, right? Laser light can produce interference fringes. Yes? We're sure. Is laser a quantum light source? So in other words, is the laser beam, is the laser light a quantum light? Okay? Okay, this requires a little thinking. And again, there's yes and there's no. Okay? Ah, a very good question. I won't tell you. That's the third topic we have not covered today. But just pick an answer. Use whatever knowledge or no, yeah. Just guess. Is laser a quantum light? Are you in the middle again?
No, I'm actually here.
Oh, okay. All right.
I was thinking about it though.
How about you guys? Are you no or in the middle? No. No. Laser is not quantum light.
Yeah, instincts.
Yes? Are you sure?
Not completely, but
Well,
I think because I know that with the stimulated emission, with which laser is supposed to be, you shoot a photon, which stimulates a photon to be released, and then you get two photons. And for the laser to exhibit the laser qualitative properties, it's about more than one photon.
mm-hmm.
It's that they are cheap and go together.
Mm-hmm.
And if there are more than one photon, it doesn't behave like a particle, but like light or a wave.
I see.
And that makes it not quantum.
Okay, you almost convinced me. I like that argument. I like the argument. I do. Yeah, there's strong truth in it. I like the argument. Okay, so unanimously no, right? Or you're not so sure anymore?
Can I change to yes?
Of course you can change to yes. That will make it more fun. Yes, so we have one yes. Anybody want to shift? Okay, if not,
I want to hear the argument.
okay, if not, then please try to convince this lady. A lady to another lady.
because last week we were doing HBT and then the value was supposed to be 2, and then if it's 2, then it means they are coherence. And I'm not so sure about the definition of quantum light because that's the point, right? And then I think I heard from Yulian that he said coherence means like how much they are quantized. And if combining these together, if we call it quantized when they are coherence, and then theoretically we should get the number of G equals to 2, which means it's in a more coherence way, then maybe it's a yes.
But you were talking about our result, right? And the graph looked like this. So we got the first like a very high peak, and then a very low peak, and then we got like a very close to 1.
Oh, I did not get the number 2 from our result by reading the manual. It's saying that's we're supposed to get 2, but because of some reason, because of the time that it's not aligned, so we only get 1. 1 means they are not coherent and they are unrelated. It's because the time alignment hasn't been reached, but it should be 2. And if it's 2, it's correlated. It's coherent. It's quantized. Yeah, that's why
I'm not convinced because in the manual it says that it's supposed to be 0 for the light to be quantized.
0?
Or like less than 1.
Oh,
I'm like pretty sure.
0 is when it's not that. Oh yeah.
Oh yeah. Duh. Okay, I give you one more chance. So second time, let's choose between yes and no. Do you decide to stay in yes or want to switch back to no?
No.
Okay. How about you, young lady?
I have no reason to believe that it's, or like I have no evidence that it can be in quantum state.
Okay.
Maybe there is.
Oh,
Okay.
the one we are doing today is the quantum light, right? The first experiment, it should not be quantum light, right? So the pair source is the quantum light.
Sweet. Very smart. All right. Please have a seat. The answer is no. Okay. And it's not because laser light is not quantized. Okay. There's a lot of vocabulary that is flying around the room, and I love it because we try to speak in another language. So we need to practice our quantum language, and that's okay. That's okay. It's good. All right. But earlier you asked a good point. So what is a quantum light? Okay. And remember in the first lecture I say the quantum nature of light shows in its particle property. Okay. So what does that mean exactly? What does that mean exactly? That means every light that you have, and this we have not talked about before, every light you have has a photon statistics. Okay, photon statistics. There's 0 photon state, there's a 1 photon state, there's a 2 photon state, there's a 3 photon state, there's a 4 photon state. And like, how does this make sense? Like, what is a 4 photon state? What is a 5 photon state? Well, you only derive this. This only makes sense after you quantize the light. Okay, so this will be covered in another lecture. But what I'm trying to say is there are distributions. Okay, if you have a distribution like this, just like pick on one of them, either this or this. Okay, if you have certain distribution that determine your quantum statistics. Okay, and for laser, the quantum statistics is like this. Okay, it's called Poisson distribution, or Poisson distribution. I hope I'm spelling it right. Okay, distribution. Okay, so this is laser. Laser has, it's almost like a Gaussian, almost, but it's a Poisson distribution. Okay, and this photon statistic does not have any quantum feature in it. Okay, so it really depends on the particle statistic of the light to determine whether this light will show quantum nature or not. Yeah, so it has nothing to do with the interference in space and interference in time. It has nothing to do with that, because the interference, again, is a wave thing. Okay, and classically, light, electromagnetic light is wave, so it certainly will have that. All light will have that. So just like I said, fundamentally, there's no reason for them not to interfere. If they don't interfere, that's probably because of technical issues, like misalignment, the width being too small, and you're not putting them together. Okay, but the photon statistic is what determines whether this light will display a quantum aspect or not. And laser having a Poisson distribution will never display a quantum. And in later lecture, I will explain like why the photon statistic has to do with quantum or not, and how does that relate to the correlation, the second order correlation measurement they're doing, and all that. These are all very convoluted. There are like 10,000 concepts involved, and they're all very convoluted. So we will have to spend a little more time than we have today. Not a little more, actually, a lot more time than we have today to explain everything. But I'm sure you, by the end of this semester, you'll be able to tell what a quantum light is, a classical light from a non-classical light. Okay? Okay, great. So thank you very much for your participation, and let's move to the lab and start our lab work today.
But I want to know now.
You want to know now? Great. Because you're writing the report, right? Yes, I know. Oh, for those of you who are so eager to learn about this quantum business, I would highly recommend reading this book, Introductory Quantum Optics by GRA and Knight. So these are English people and English physicists. This book is great. This is the second edition. I like the first edition better. But anyway, on chapter 5, there's quantum coherence function. And what we cover today is basically half of this chapter. So you should be able to understand some if you read it. And you NTHU, if you're on the NTHU network, you are able to download this book online from Cambridge. So Cambridge University Press, yeah. Okay, so you can either borrow this book from the library, a physical book from the library, or you can read it download a PDF online. Okay. Chapter 5.